Good morning. We have discussed this stick diagram for describing a circuit, MOS inverter circuit, in the last class, and we shall apply today the stick diagram approach to that will draw the logics, different logic gates using MOS inverters. For example, let us consider standard NOR gate. Standard NOR gate. Okay, please keep silence. This is a stick diagram of a standard NOR gate, static nMOS NOR gate. Remember, I told you that the blue lines indicate metal or conductors, green lines indicate diffusion or implantation, and red line indicates polysilicon. This I clearly discussed in the last class. If a green line and a red line, that means a poly and diffusion, they cross over, it indicates that at the crossover point beneath it there is an nMOS state. On the other hand, if there are crossovers of other lines, no such thing, we don't assume anything, that is below this there is nothing. And if there is some cross at the cross point, some cross mark at the cross point, that indicates that there is an electrical connection between the two, and we call it cross cut. And accordingly, you see that this is the nMOS NOR gate using an HMOS kind of thing, whereas where HMOS is enhancement mode driver universal, whereas depletion mode load. That yellow dot around this intersection indicates the transistor here is not an enhancement mode transistor, it is a depletion mode transistor. And that is why this red line, that is a polysilicon, is intersected with the, that here I have put a cross. Of course, this plot should have been in one other color, normally black, but I have not used that. In fact, all the crosses should have been indicated in a single color, usually black, but I have shown, but this cross indicates there is no transistor. If there is no cross, it means that there is, in the intersection of poly and diffusion, there is a transistor. But if there is a cross, it indicates there is no such transistor, there is simply, in that case, poly and diffusion, they are nothing but some, some interconnect levels, and they are connected at that particular point, okay? And this is the input, and this is the input A and B. and you get at the output. Normally, I have shown it, the output is shown by diffusion because I'm assuming that the whole circuit is only a part of the circuit. Only a part of the circuit. In actual technology today, of course, we do not extend diffusion line like this. Because in that case, the capacitance of this diffusion line will be too high and there will be a lot of delay involved. So therefore, what we do normally, from this point, there is another metal line with a cross, which I indicated in the last class, which goes to the input of the next line. Means this metal will have a cross cut with similar poly line in the next stage. Okay? And in the conventional way, which I will prefer to draw in this class because of your convenience, you don't have so many colors. Here the conventional thing is simply like this. This is the metal. See, let me write. This is VDD. This is ground. Similarly, this is VDD. This is ground. And we are following a convention. The solid line is our diffusion. So it is like this. It is like this. It is like this. And dashed line is poly according to that nomenclature. And because this is a depletion mode transistor, I will put a square around it. All right. Similarly, this is A, this is B, and at this point you get A, B, NOR. Let me write once again these things, whatever I have written here, and I think you know what are they. These are nothing but the W by L ratios of the three transistors. It is the usual way of writing it. This is a ratioed design. I told you that there are two kinds of approaches. One is called ratioed design for logics. The other is ratioless design. Okay, we shall be coming to that ratioless design afterward. Whatever logics, whatever inverters, whatever static gates we shall discuss after, for a few classes from today, it will be mostly static logic, and therefore you know that these are all ratioed design. These are all ratioed design. You know that if 1:1 is the W by L is just merely ratios. Please don't assume that normally what is done, channel length is kept the same. It is a W which is adjusted. Please remember that is a tendency. Today's technology demand. Earlier it was not like this, because earlier all MOSFET logic was limited to several megahertz. Okay, and there you could have a larger L also. You could adjust both L and W. We did not bother much about the intrinsic device speed. But now we have to bother about the intrinsic device speed simply because we are now designing our MOS ICs at very high operating frequencies. And the standard today is to assume that the channel length of all the transistors identical, the same. It will be, if it is 1 micron, means all the depletion mode, driver, load, everything is 1 micron channel. Then W is to be adjusted. Simply W is to be adjusted. Can you tell me, if such a circuit is in the output stage, how do you select the value of, suppose 1 micron is the channel length, assumed for the technology, particular technology. Now, there are two. One is the logic circuit is internal, intrinsic, whereas there will be something at the output called buffer. It is usually called buffer. In that case, how to choose a value of W? I said L is fixed, 1 micron. W? How to decide that? It is clear that higher is the value of W, more will be the conductance, more will be the transconductance, self-conductance as well as transconductance, and therefore the drivability, driving capability of the MOSFETs will be higher. Therefore, it is natural that in the output stage, W will be much larger than in the core of the circuit, in the core of the circuit. So here, if I said 1 by 1 means is just a value. Don't assume that L is W by L. So that way it has been written. So you just see now the two driver transistors which has to be used in the case of a NOR logic. they have the same W/L ratio compared to, so here what is the value of beta R for this inverter and for, there are two inverters in a merge, is it not? In NOR logic there are two inverters merged. What is the beta R ratio of this, beta R of this? 4. What is the beta R of this? 4. Is it proper? You remember it is a MOS logic with depletion mode load. We don't require a high beta R. Typically around 4, 5 I said, it has been, the example is full. 4 and 5 normally does serve the purpose. But if it was a saturated load, naturally this same thing would have been some 50/1. Please remember this. Okay? Now I have assumed the same W/L ratio for both the driver transistor, and that is 4, the optimum value. Is it logical? Is it logical? It is logical, because if any one of the transistor is on, the output will be 0. That means it will be a NOR of, that is how it is a NOR. Two switches are in parallel. Therefore, it basically is OR, and because of this load transistor, it becomes inverted. As you know, if there are two switches connected in parallel, it provides you OR operation. Switches connected in series provides you AND operation. But in this case, because I am using in an inverter fashion, there is a load and driver, automatically that thing becomes inverted. So you are getting ORing of A and B, and then a NOT, an inversion. So in this case, because in a single operation only these two transistors, when this is off, these two transistors are, so at least you know that we have to maintain suitable W/L ratio to achieve the, you know, that the output impedance as well as output resistance as well as the logic swings and noise margin. But suppose both of them are on, still better. It is 8:1. Effectively, it is 8:1. So if we are using NOR logic approach, you know the NOR logic is a universal gate. NAND logic is also a universal gate. So if you are using only NORs, then you are expected to achieve a higher packing density. Let us now go to the NAND. ANDing means simply connecting switches in series. As you know, we have already studied, it's a very most starting knowledge, you know that this connecting switches in series is equivalent to AND operation, connecting switches in parallel equivalent to OR operation. But because of the load transistor here, again it is inverted, so it gives you NAND. This is a common knowledge to you. But you note that this is now 8:1 and 8:1. 8/1, 8/1, whereas this is 1/1 as it is. Why? This is AND and NAND, basically the same, only the inverse of that. If one of them is 0, that's the property of AND. If one of them is 0, the AND is 0 or NAND is 1. So one of them 0 means the circuit is off. If any one of the MOSFET is 0, that is, if the input to that MOSFET is 0, the transistor is off, so this line is off. If both of them are on, then only you get, okay, If both of them are on, then what happens? Output is 0. But when both of them are 1, suppose this is 4:1 and this is 4:1, what will happen? Suppose the W by L ratio of the two series transistors both are 4:1, as in the case of NOR inverter, NOR gate. What is going to happen? Effectively, both the transistors combined will offer you 8:1 W by L ratio. 4:1, 4, because the two resistances will be added. Yeah, I'm sorry. You're right. No, register. Yeah, you're very much right. 2:1. Yes, 2:1. Definitely. It will become 2:1. Resistance will be added, and therefore you have to have the individual transistors with W by L ratio 8:1, so that after the both of them work together, then effectively it becomes 4:1. So you maintain the noise margin, you maintain the logic swing. What is the drawback of this? More area, less speed. More area, less speed, and all, because after all, therefore this AND kind of operation we should try to avoid as most as possible, as best as possible. We should try to depend more on OR and NOR rather than ANDing in MOS logic. I think this is very well known to you that TTL is naturally a NAND gate, whereas ECL, nMOS, CMOS, etc., they are naturally NOR. If you want to utilize, if you want to realize NOR from TTL, it becomes more complicated. Can you tell me, suppose one input is floating, it is equivalent to 1 or 0 for TTL? 1. Whereas for this case? 0, because you are not applying any voltage. Of course, if there is pickup, you will have a problem. But if suppose it is properly screened, is very properly screened, and you have kept it floating, means it is this transistor remains off. Only by applying a voltage, you turn it on. That's the basic things of nMOS. Please remember this. nMOS is nMOS circuits, they are field effect circuit. Therefore, you have to apply voltage. You don't draw any current at the input. But you remember the TTL. You have to sink in current. Either the current is 0 or you are sinking the current. Application of a voltage there means the current is not. We are not drawing the current. Otherwise, if the input is grounded, in the case of TTL, you are shrinking the current. So in this case, it is just the opposite. This should be kept in mind. So these are very simple. That way, you know that you can realize any other kind of logic. For example, let me do this thing. AND, OR, invert. Very simple. You can just try to draw yourself. You can try yourself instead of looking at this diagram, whatever I am drawing. Anything you can try yourself? Again, if this is 1 by 1, 8 by 1, 8 by 1, 8 by 1, 8 by 1. If it was AB plus C invert, then simply one transistor with 4 by 1. If it is AB plus C invert, then one transistor here and with the ratio of 4:1. And you see that how easy to draw the circuit diagram using this stick diagram approach. Of course, I am dependent on single color here for your convenience, but normally it is done with using the proper colors. Standard softwares are available today, particularly for nMOS logic design, where if you give the circuit description, it will quickly draw the whole circuit in stick diagram. And then once the stick diagram is known, the layout becomes very simple. From stick diagram to actual physical layout on the IC, this transfer is very simple if the stick diagram is drawn. This has to be kept in mind. This way, you can. This is the standard AND or inverse circuit. You can draw. Say, can you try yourself an exclusive OR? Please try it yourself. Exclusive OR circuit. Draw the stick diagram of an exclusive OR static inverter, static nMOS inverter. I forgot to show this one. Please remember that in the exam, just not showing a cross here will really give you a lot of, that deduction of marks. Should be careful. For me, no problem. I can make always errors and correct. Exclusive OR. I want exclusive OR here. You see, in this case, simply you do the following. Here you apply A, here B, here A inverse, here B naught. Automatically this becomes A, B plus A bar, B bar. What is this? Exclusive NOT, so it's invert. Or you can A bar, you can in the conventional way also you can draw, but you need another inverter in that case. A B bar plus A bar B, invert, invert. You need another inverter in that case.
But in the A bar part, you just write A bar or inversion.
No, you know that again, yeah, you are right. You are saying that A has to be inverted, B has to be inverted, but it is normally assumed this is only a part of the whole circuit. So whenever you are applying A, B, C, D at the input, there is always an inverter chain. Let me show you like this. Normally, whenever we configure a chip, always say this is A, B, C, etc. We always put an inverter at the input. At the very beginning, so that you get not only A, B, automatically you are getting, this is A, B, C, etc. You get A bar here, A here, A bar here, B here, B here, C here, C here. So these things are available. ABC means automatically their complements will also be available. That is the presumption. Any chip design involves that. At the input I/O circuit, in the input side, this is done. The standard practice. So don't worry about that A inverse and B inverse, the complements. They are available. They are readily available. So this is the most compact form. If you want to use the normal conventional A B bar plus A bar B invert, then naturally another inverter will be needed. So we avoid that. So that's how that. Let us not go into the details of, because this is very standard thing, and you can design any combinational logic, any complicated combinational static logic using the same approach, I don't think you have it needs any further discussion. Only things to be kept in mind is that if it is not, it is convenient because it leads to higher packing density. You don't have to bother about the bigger transistors for the driver. On the other hand, if it is ANDing, anywhere you do have to AND, but you can't avoid. Whenever you develop a full big combinational logic, it is rather impossible that you can do it because you know that NAND and NOR are universal logic. So any combinational logic can be developed using NOR logic, NOR gate or NAND gate. But if you take that approach, sometimes it is found the number of blocks may be very high. So in order to minimize the logic, we also need to minimize the number of blocks. And sometimes it becomes inevitable to use AND also. So, but you try to keep in mind that our number of NAND gates or AND gates should be minimized in the design if you want compaction. Okay? Now, before I pass over to the next topic of discussion, I will discuss quickly some, you know that they call pass transistors or sometimes also called transmission gates. We first consider an inverter. Let me draw in the old fashion. I'll take help of this stick diagram afterward whenever required. But for the time being, I will use the standard diagram. This is called an inverter with a steering gate. An inverter with a steering gate. You see that here, this transistor at the input of the gate is nothing but a switch. It is called a MOS switch. It is a single channel MOSFET switch, nMOS switch. Okay. Now let us see that how it functions. When you please note that this is ground, this is also ground. Substrate is grounded for everything. Everything substrate is grounded. This is single channel inverter. The substrate is grounded. So all NMOSs are developed on the substrate and substrate is grounded. And the source of the driver is also grounded. This is to be kept in mind. If Vi is initially, let us see, Vi is equal to 1. And let us assume that the steering gate, I have to apply a Vg. And Vg is equal to 0. What is going to happen? And this input, let me call it now Vi dashed. Then what will be the value of Vi dashed? When Vg is 0, then this transistor is off. Okay, this transistor is off. Now, if Vi dash, it depends on the initial state. If Vi dash was 0 in the last state, then it will retain that 0 state. But if it was 1 in the last state, it will retain in the 1 state if you don't wait for a long time. That means if there is a clock, the Vg is applied in the form of a clock pulse of relatively higher clock frequency, then what will happen? Because this is a MOSFET, this input capacitance is a very low loss capacitance, actually an ideal capacitance. And when this transistor is off, whatever charge which was stored earlier, that will be retained for some time. And you know the charge and voltage are related. If charge is 0, voltage is 0, charge is high, voltage is high. So if it was in the one state, that one state will be retained. If you don't wait, that means if the clock pulse is, clock frequency is not very, very low. Okay? But you know, otherwise, if I assume that this input is always, there is a mechanism by which it is always discharged, then it is assumed that Vi dash will be equal to, sorry, Vi dash will be equal to 0. That means the input will be Vi dash, sorry, what I am saying. Vi dash will be 0 or 1 depending on, as I told you, depending on what was the earlier state of this. Now, what I want that when I Vi is 1 and Vg is also 1. 1 by 1 is normally, it is VDD. And by Vi is 1 also means VDD. Because this is a depletion mode, this is a HMOS logic, the output VOH will be VDD. So 1 means VDD. And 0 means almost 0 volt. Please remember. VOH is, in this case, VOH is equal to VDD and VOL is almost equal to 0. Vi is 1, Vg is also 1. In that case, whatever may be the earlier state, this will go to what? That is the question now. That is the question now. It will become 1, but what will be the level? This is the question now. Will it be VDD or different from that? If it was VDD, it is most desirable. VDD minus VT, because you see that this transistor, in that case, this is VGG, this voltage and this voltage is the same. So this transistor is in saturation. And if this transistor is in saturation, then when the current through the transistor is 0, you remember the voltage which is developed at the output node is VDD minus VT. We have standard thing. So this will become VDD minus VT. Keep in mind that this becomes VDD minus VT. This is a very important thing to be kept in mind. That means the output gets degraded when the switch is on. The full swing is not available here. And as a result, what is going to happen? If I want a full, when the switch is on, whatever be the state here should be transferred. If it is 1, I want that 1 should very reproducibly, very faithfully go into that point. But here I am finding it is not totally faithful. There is a degradation of that. The level earlier here it was VDD, but it now becomes VDD minus VT. So what will be the bad effect of that? This transistor will not be that heavily on. I want that this transistor should be turned on very properly. Corresponding, the resistance offered by this transistor under on condition should be very low, so that its output voltage is very small, almost 0. But if you can't apply that full 5 volt, if it is degraded by say 2-3 volt, which is the 1-2 volt or 2-3 volt, the value of VT, then it will not be turned on to that the inversion layer which will be formed in the channel will not be that strong. Its resistance will be higher, and as a result, VO will be increased. The logic says swing in the 0 end, NN0 will be affected. And for that, what is to be done? I need to design this transistor. If it is designed like this, 1:1, and this is 4:1, this 4:1 normally does not serve the purpose. It is preferable to make it just double, in order that the logic swing does not suffer. Similarly, when Vi is equal to 0, Vg is equal to 0, then Vi dash is uncertain. 0 or 1, uncertain. It depends on the earlier state. However, we want, because the clock logic, in the clock logic application, whenever clock is applied, then only we count it. Before that, whatever may be the state, we never consider. Only after the application of the clock, this synchronous logic, you remember, whatever is the state, that is the desired state. So this is not important at all. This one is not important. However, when Vi is equal to 0 and this Vg is 1 means again VDD. In that case, this transistor is properly on. Am I correct? Please see that this is very, Vi is 0, Vg is 5 volt or VDD. What will be the status of this transistor? Which one is behaving as source and which one is behaving as drain now? This one is behaving as source. This is 0 volt. And therefore, this transistor, we have applied a voltage at the gate which is much above Vt. It is very properly on, it's deeply in linear region, so this voltage will be, whatever charge which was there earlier in the last stage will discharge very properly. So it is assumed Vi dash is equal to 0. So this, there is no problem here. When Vi is in a 0 state, there is no problem. Whenever Vi is high, then there is problem. Okay? So this is a very important thing. Such a transistor is normally called a pass transistor or a MOS switch or a transmission gate, and this forms the part of all modern dynamic logics. We shall be discussing that afterward. All modern dynamic logic, these transmission gates are very, very important. They form very important parts of all that. But please remember that whenever you are using a single channel inverter, single channel, just nMOS kind of switch, nMOS kind of pass band, what is called the pass transistor. In that case, there will be a deterioration of voltage level, and to rectify that, we have to adjust the W by L ratio of the driver appropriately, and which will ultimately lead to less packing density. This has to be kept in mind. Okay? But let us see that using CMOS, there can be a lot of improvement called CMOS transmission gates. Just a minute. CMOS transmission gates. In this case, what you do a very simple thing. Now look at this very simple circuit carefully. You'll find that there is a difference of this one with respect to the CMOS inverter. In CMOS inverter, the nMOS and PMOS, this is nMOS and this is PMOS. They are connected in series. PMOS acts as, usually PMOS acts as load and NMOS acts as driver. But in this case, the two MOSFETs developed, one developed, NMOS developed on the substrate, PMOS developed on the tub, NWell. They are connected parallelly, in parallel. Now we apply a clock pulse like this, C here and its complement here, inverse here. Then if you apply an input signal, it can be transferred to the output, can be passed or may not be passed depending on the state of the clock. If C is equal to 0, this is open. That is why it is called a normally open switch. Please note that this is grounded. And the PMOS, usually in the case of PMOS, the NWell cannot be kept grounded, isn't it? NWell is all floating. So what is done? NWell, one end of NWell and one of the two diffusions, P plus diffusions, either source or drain, whatever you call it, is grounded. It is not grounded, it is connected with that NWell tub. That's the only difference with, that I told you that MOSFET is a bilaterally symmetric device, and that leads to higher design advantage. I have clearly mentioned that earlier. Compared to bipolar transistor, which is totally asymmetric in nature. Emitter and collector, if you interchange, you will not get the beta and all these good properties. But for MOSFET, there is no problem. But is it totally asymmetric? No, because always we put, if it is source, at the source end of the driver, you remember what you do. That source is connected with the substrate. And that makes it asymmetric in that sense. Once you short the source with the substrate, you cannot no longer use it as a drain now. That source cannot be used as drain afterward. So please remember, this is not a problem in the initial layout stage. In the initial layout, you can always keep drain this side, source this side, or vice versa. But at the end, now decide that which one is convenient, keeping the source on the other side or this side. Accordingly, give a little space, open a small window on the substrate and connect it. But otherwise, design is very compact. But that is not permissible for bipolar transistors. Once it is designed, you cannot interchange emitter, particularly for vertical transistors. You cannot interchange emitter and collector. Please remember this. So here, this is grounded because NMOS is usually in PMOS, in NWell technology, NMOS is developed on the substrate. So substrate is grounded, this is grounded. But what about the PMOS? In certain design, this thing can be kept also floating. And in certain other cases, source, so-called source, one of the two diffusions, is connected with the NWell, which I have shown in the last, when I discussed the NWell construction, I showed it very clearly. So this may be connected either with this side or usually it is connected with this. I'm not showing, but it can be kept floating also. There are various designs. The substrate has to be kept grounded from noise point of view. Substrate should not be kept floating. It should be grounded. At least there should be a very good AC ground for the substrate. Otherwise, there will be floating noise. So this should be kept in mind. Now you see that it can be, if C is 0, this transistor is off, naturally. And what about the state of this transistor? C is 0 means C bar is 1. C bar in 1 means? You know that it is a positive logic. I am never applying a negative voltage. It is a positive logic. So 0, 1 means, if it is 0, 1 means it is a VDD is positive. But this is a PMOS. Only applying at the gate voltage something negative volt, more negative than VT, it will turn on. Otherwise, it will remain off. So this will also remain off. So nothing will go. So when C is 0, the switch is open, very properly open, no problem. Now when C is 1, initially suppose the output was in the 0 state. Normally, in most cases, we arrange that. We discharge the out. This is called setting. We do set, reset, etc. Normally, by setting means everything is turned down to 0 volt. So there is some arrangement in the circuit. Suppose it is in the 0 state initially. Then if input is high and clock is high, then what is going to happen? Input is high means, again, in CMOS logic it is VDD. And clock is high means, therefore it is also VDD. Please keep in mind. So this is VDD and this is VDD. What is going to happen? This transistor will be again in saturation. It will be on, but it will be in saturation. And we expect a voltage. What is the voltage now? Again VDD minus VT. But this will be counteracted by this PMOS, which will be very heavily on and in linear region, and will help in the passing of the entire voltage. You can check it yourself. When C1 is high, C is 0. C is 0 means this is 1. So with respect to this is negative. So this transistor is very heavily on. And this is 0. It is strongly in linear region, and it will pass the whole voltage without any problem. That is why CMOS transmission gate does not suffer from that voltage degradation problem, which is typical of nMOS switches. Yes.
We don't need this nMOS gate. PMOS is
no.
Basically
CMOS will not. The same problem will happen. If you take a single channel inverter in one side, it will know. The same problem will happen. You just think of it. If you use a single channel inverter, firstly, using PMOS, you have to use a negative logic. This is a problem. You have to use a negative logic. And secondly, using nMOS, combining PMOS with nMOS only you can get this advantage. Not in the other fashion. You can easily see that what will happen for the other switch. It's the same thing, but only depending on the application of the clock. These are the symbols of the normally open and normally closed switch in CMOS technology. Here is the same circuit, only thing is here at the clock, at the nMOS input gate, we apply the inverse of the clock. So when C is 0, C bar is 1, so this transistor is on. Okay, this transistor is on, it passes it, but unfortunately this is VDD and this is also VDD. 0 means C is 0 means this is normally on, that is why this is normally closed. So again, we expect that the voltage will be degraded. If it is VDD, it will come, if this PMOS was not there, it will degrade to VDD minus VT. But in this case, what has happened? When C is equal to the same thing, exactly the same thing. C is equal to 0 means this is 1 and this is 0. And this side is high, that means this is effectively at a negative potential with respect to this. Okay?
We don't have the nMOS at all, just the PMOS. There's a PMOS to do that. So then C is 0. Then with respect to input, this is highly negative.
No, this C is, this thing is going to, this is a steering gate. There is no regular voltage supply in the other side. Please don't forget that. This is just, it is something like floating. Don't forget that. If you are thinking that using PMOS you can achieve, it is not possible. It is just not possible. You think of it and then I think answer. You will understand yourself. Either use PMOS or nMOS. In the case of PMOS, you have to use negative. You can use positive logic, only the logic levels will be negative voltage and 0 volt. That is usually the process. It can be a positive. You can think of in terms of positive logic, but it will be complementary of that. Otherwise, CMOS will normally give you a negative logic. What is the drawback of that PMOS? No question of drawback. Using PMOS, you can develop, because enhancement mode transistor, no problem. You will get negative swing at the input, corresponding negative swing at the output. But levels will be something, some 0 volt or some voltage to a negative value. VDD has to be a negative voltage with respect to VJ. Similarly, VG has also to be a negative voltage with respect to the source. You just see that in this case, I think I have done this one. PMOS in this, these are floating on N wells. And if you connect in this side is always behaving as the source side. This side is always behaving as the source side. Whereas in this case, this side is behaving as the drain side. And that's normally the case for normal CMOS. You just try to remember the, sorry, time is over. You just try to remember the CMOS inverter. The bottom, the diffusion at the bottom is source of the nMOS, whereas the diffusion at the topmost point, again the source of the PMOS. That way it is just opposite kind of thing. Exactly that is shown here. The substrate means here, this is not substrate, this is the N well. Please remember, whenever I draw PMOS, it is sometimes preferable to draw a block. This dashed rectangle indicates N well. This N well is shorted with the source. So this is the source side. This has to be kept in mind. So you see that in the next class, I will discuss about how to use these switches to develop logic circuits. These are called fast transistor logic. There are various MOS logics developed. So one form of logic is called fast transistor logic. We shall discuss in the next class. Thank you.